Let's examine some key points about symmetrical and asymmetrical encryption. Symmetrical encryption we also call private key or secret key cryptography, and it uses a single key to both encrypt and decrypt the data. It's also referred to as two-way cryptography. A single cryptographic key is used to encrypt and decrypt the information. Understand that it is totally dependent on the key remaining private. If we want to transmit an encrypted piece of data, the sender encrypts it using the private key. The receiver decrypts it using the same private key. It's very efficient. It provides very strong encryption protection, provided that that key has not been compromised and has been kept a secret. The difficulty is using symmetrical encryption on scale, that is, between many people. If only two people need to share the encryption, a single key is required. However, if we look at the formula shown on the screen, n times n minus 1 divided by 2, we can calculate the number of keys that are needed to be used if we were to scale this up between users. Let's bring up our calculator on the screen. So if I have 4 users and we want to be able to use private key symmetrical encryption for all 4 users to exchange data, I would take 4 minus 1, and that equals 3. I would divide it by 2 and multiply it times 4. I would need to manage 6 keys for those 4 persons to be able to exchange private data. Doesn't sound so bad. But what if I have 40 users? Well, those 40 minus 1 divided by 2 times 4, 0, 40. Now, for 40 users to be able to exchange data using symmetrical encryption, we would have to manage 780 separate keys. It gets to be very cumbersome, impossible to manage. What if this was a website and you were attempting to do this with your users and you had 10,000 people attempting to access your website and you wanted to do it securely? Well, you can see where this goes. Minus 1 divided by 2 times 10,000, almost 50 million symmetrical keys to manage. Impossible. However, it is very efficient for encrypting data, especially data that we're storing. One of the first symmetrical encryption algorithms that was developed was DES, Data Encryption Standard. However, it was broken in 1999. At the same time, in that same year that it was broken, Triple DES was released. It took the original DES standard, which was a 56-bit. Let's take a look right down here. Key size. This is the key that is used to do the encryption, 56 bits. It's based on a 64-bit block, and the key size is 56 bits. So what they did was they took that 56-bit key size and did it 3 times. Triple DES, it's also a symmetrical algorithm, and it applies DES 3 times. There's 3 different combinations in the way that it can be done. It's still being used. All 3 keys might be unique. Key 1 and key 2 are unique, but key 1 and key 3 are the same, or all three keys could be identical. The encryption process is done either using 2 keys or 3 keys. In the first process, encrypting is done using key 1 and then key 2 and then re-encrypted using key 1. It could also be performed encrypting using key 1, decrypting it using key 2, then re-encrypting key 1. If we're using 3 keys, it could be encrypted using key 3, encrypted using key 1, key 2, and then re-encrypted a third time using key 1. Alternatively, encrypted using key 3, decrypted using key 2, and re-encrypted using key 1. Like I said, triple DES is still in operation, but not as prevalent as it used to be. Advanced encryption standard, the Rijndael cipher, as it was originally known, was selected as a successor to both DES and triple DES by the U.S. government. It was included as a standard by NIST in 2001. The federal government still utilizes this. It uses a 128-bit block size, and it can have either a 128, 192, or 256-bit key. Note that all 3 key sizes are adequate to encrypt classified information up to the secret level. However, the 192 and 256-bit offered encryption strength for top secret information. Also used is IDEA, International Data Encryption Algorithm. It uses a 128-bit key based on 64-bit blocks. There's also CAST 256, Blowfish, Twofish, and RC5. These are all block ciphers. RC4 is a stream cipher. If we look at our chart here, these are all block ciphers. AES, DES, triple DES, IDEA, Blowfish, Twofish, RC5, and CAST. All block ciphers. We're going to talk about the difference between a block cipher and a stream cipher in just a second. Note the various key sizes. Always remember that if you see a question that asks what block cipher uses a 56-bit key, the only one is DES. Which one uses a 168-bit key? The only one is triple DES, 56 times 3. Note that a number can use 128-bit keys. RC4 is a stream cipher. Let's take a look at the difference between a stream cipher and a block cipher. A stream cipher encrypts one character at a time. It's much faster than a block cipher because it just continually encrypts the data character at a time as long as that data is flowing. The block cipher does blocks of data. It operates on larger blocks at a time. That means it's a little bit slower. That's the key difference between a stream cipher and a block cipher. Stream cipher is more suitable for a hardware implementation. So for example, you could use it for a secure web connection. Block ciphers are typically used in software, database, and file encryption. So for example, encrypting your hard drive. Asymmetrical encryption we also refer to as PKI, Public Key Cryptography, Public Key Infrastructure. It makes the use of 2 keys. It's much more versatile. If I want to have someone connect to my website, and let's refer back to that previous example. If we were using symmetrical encryption and we had 10,000 users that wanted to connect securely to our website, we had to manage almost 50 million keys. With symmetrical or asymmetrical encryption, we hold the private key and anybody can have our public key. Because only we can have the private key, any user who can create the relationship between the public and private key knows that we are the legitimate website. The private key is generated first, and it in turn generates the public key. It's referred to as a one-way function because although the private key generates the public key, it doesn't work the other way. You cannot use the public key to regenerate the private key. It's mathematically infeasible. So let's take a look at an example of public-private key encryption. So for example here, Bob and Alice each possess a public and a private key. It's critically important that each individual must keep their private key secret. Asymmetrical encryption. All encryption is based on the keys staying secure. Encryption algorithms should be publicly available for inspection. The algorithm. That is how it's determined that the algorithm, the mathematical process, is secure, is correct, doesn't have flaws. The keys that are generated using that process are what needs to be kept secret. So, for example, if Bob wants to send Alice a message and wants to prove that it's from him, he encrypts it using his private key. Anyone else can have the public key, so anyone that receives the message that's encrypted using his private key and they have a copy of his public key are able to encrypt it, and they know that since only Bob possesses the private key, it must have come from him. Proof of origin, non-repudiation. That is what that represents. It does not indicate confidentiality because anyone with the public key can decrypt it. So here in our example, Bob encrypts his message with his private key. It's a secret key and only he knows it. He transmits the message to Alice. Alice then decrypts the message using Bob's public key, which he freely distributes. Just as I previously said, Bob has encrypted the message using his private key. So the message can be decrypted by any person with the public key. So this is not secure encryption. The message has been encrypted, but a man in the middle attack can easily decrypt it because his public key is freely available. It's used to provide proof of origin, non-repudiation, knowing who it came from. Now, in most cases, proof of origin as well as confidentiality of the message is required. To do this, the message is encrypted twice. So if Bob is sending a confidential message to Alice, encrypted with his private key, he's providing proof of origin and confidentiality by doing the following steps. He encrypts his message using his private key. That is the proof of origin port. He's the only person who has access to his private key. He then in turn encrypts the message, the same message that's encrypted using his private key, he encrypts it using Alice's public key. This provides confidentiality because Alice is the only person who can decrypt the message because only she holds her private key. Upon receiving the message, Alice first decrypts the entire message using her private key. Since it was encrypted using her public key, she's the only person that can do this. Confidentiality. She then decrypts the message again using Bob's public key, and since only Bob could have encrypted the message using his private key initially, only that public key can decrypt it, and this irrefutably proves that Bob was the sender of the message. This provides proof of origin, or what we call non-repudiation. Additionally, we can use digital signatures to sign messages. A digital signature provides both proof of origin and message integrity. The message integrity is the function of proving that the message didn't change. Same thing, it's a hashing sequence. Same thing we use to prove that a file on a website has not changed between it being placed on the website and you downloading it. It's accomplished by passing the original plain text message through a hashing algorithm, and this creates what we call a message digest or hash value. That is then encrypted using the sender's private key. By encrypting the message using the private key, the sender's providing the proof that they're in fact the sender. The hash that's been encrypted provides the fact that it hasn't changed. Let's take a look. The steps that Bob would use to digitally sign the message. First, he would hash the plain text message to come up with a hash value or the message digest. He then encrypts that hash value or message digest with his private key, and here's an illustration of it. So the first step is hashing the message using an algorithm. The hash algorithm produces the message digest. Bob then encrypts the hash with his private key. He attaches the encrypted hash to his message. And at that point, he now has the message that he can provide proof that only he sent it and proof that the message has not changed. The digital signature doesn't provide the confidentiality part. Encrypting it with his private key does. If he wants to provide the confidentiality part, I misspoke. The confidentiality part comes from the fact that he would then in turn encrypt it using Alice's public key. Because only she can decrypt it using her private key, that's the confidentiality part. So she would receive the message, she would decrypt it using her private key, knowing that it was confidential because only she can decrypt it, and she would then be able to decrypt using Bob's public key to be able to examine the text and decrypt the encrypted hash to compare the digital signature and verify that it hadn't changed. Because of all these steps, asymmetrical encryption or asymmetrical cryptography is much slower than symmetrical, but it scales much easier. So some of the most widely used solutions are RSA, Diffie-Hellman, L-Gamel, and elliptical curve cryptography or ECC. The most famous of these is RSA, still in use today, and it was developed all the way back in 1977. It still has mainstream use. So understand that the RSA algorithm is based upon the computational difficulty of factoring large prime numbers. A lot of math. It's all about math. So hopefully this gives you a little bit better understanding of the difference between asymmetrical and symmetrical cryptography and where we use it. Thank you very much.